So we move on to George, that perfect on time, well, a minute on type-safe dynamic placement, please.
Yeah, all right. Well, good morning, everyone. So this is a joint work with Pascal Weisenburger and Guido Salvaneschi. We're from the programming group at the University of St. Gallen. So the title is a bit of a mouthful, so I'll go through, first of all, telling you what the dynamic placement bit is, because I hope you all like type safety. So what is dynamic placement? When we're making distributed systems, for example, systems that support caching or geo-replication, hybrid cloud, what we care about is getting the source of the resources. So where do we put them? Where do we get them from? And these decisions are often dictated by runtime decisions, like caching, how often is a particular resource being used? Should I get it from the cache or the database? It's basically based on these sorts of conditions. And we want to encode these systems safely, which means that we would like to get the data from places we know we have a tie to or a connection with. So, okay, we looked at what kind of safety does the actual literature provide us already. There's a myriad of papers already published around architectures, multi-tier programming, placement types, choreographies. They all have one thing in common, which does not address dynamic placement, is that placement is often a static property. So once statically you have decided the placement of a resource, it is set. It cannot necessarily change anymore, which means, or not change, but you don't have uncertainty in the placement. So dynamic placement is kind of not solved using these problems. So good for us, because that's a project. And so now we want to have safe placement and dynamic placement. And this is what this paper is about, where we took the framework of placement types and we kind of tried to achieve both of these things. But I guess not everyone here is familiar with the placement types, so here's a little background. This is a particular architecture, but most importantly, this is an example architecture. So you can choose any architecture you want, but for the sake of the presentation, it's just this very simple one. There are some clients, there are some servers, but they are all tied in this particular way, which is every client is tied to a single server. Servers are tied together in any way they want, and they can connect to any client as well. But since we're programming, we cannot give this to a compiler. So there's a DSL for Scala that we've implemented, in which you can specify these architectures. So that this line of code says there's a peer type called client that connects to a single server, and there's also a peer type called server that connects to a multiple client and a multiple server. This essentially encodes this architecture. But let's actually use this architecture. And for this particular program, let's decide to place a string on a client, so that every client now has a string, and let's just assign it to greetings earthlings and call it message. In the type, you see that not only it's a string, but there's also this annotation that says that it is on a client. So after I compile my program, this variable will only exist on the binary that is supposed to be run by the clients. We can also do the same for functions. So this hash messages function takes a seed and is placed on a server. So it's only callable from a server. And what it does is just goes to the clients, hashes the clients using that seed. But it's a bit ambiguous where the computation should be, and we also want to make explicit what is being sent over the wire, which is why we surround that piece of code by essentially the context in which it should run, and we explicitly say which values are sent over the network. But this is essentially just placement types. It does not have dynamic placement, which is what this project is about. So how did we do this? We followed this methodology that we kind of adopted for a while about placement types, which is we take ideas from type systems and we try to put them into placement types. In 2018, with Scala Loki, we introduced these placement types as analogous to just general basic types, which is what I've shown you in the previous slides. 2019, we took the ideas from parametric polymorphism to also parameterize some architectures, and we call these polymorphic modules. And then we kept in line with this methodology to give a treatment for dynamic placement. And what you see here are some examples of dynamic placement, like database or cache. This is supposed to model stuff which is cacheable. And the solution that we took from type system is union types. And this is what this paper is about. And so the key idea is that if we take union types and we introduce union placement types, then we can statically capture placement uncertainty, which is what dynamic placement is about. So on a type level, how does it work? We introduce a type called just a type at P or Q, where P and Q are peer types. And this, again, is supposed to represent static uncertainty, because at compile time, we don't know whether this is a thing that's at P or Q, but dynamically at runtime, we do know, because well, it's compiled with it's happening. And so at runtime, we can eliminate some of these checks, which could be bad. And this is at the type level. At the term level, this is a particular decision we went with, which is that the inhabitants of these placement types are just remote references. We introduced them with just a keyword called remote ref, and remote is there just as a reminder that these references can cross network boundaries. So you can move around this reference, and it still points to where it's supposed to point. And as an example, this particular function reads from a cache. It takes a key and returns a pointer to some value on a cache, but itself, this functionality is located on a cache. So this is the first class from the title of the project. But this is how we introduce them, and then to eliminate them, we just use a deref as usual. But the trick here is that there's also an architecture, so we know whether we're dereferring from some peer onto some peer, so we can check whether the architecture does specify a connection between these. And we can prevent them at compile time if we know no such connection exists. To introduce the unions, we just use subsumption within the Scala DSL. In the formalism in the paper, however, we have an explicit expression that can broaden the placement of a particular reference. And so this is adapting exactly the same expression from the previous slide, except now read from cache, instead of returning a pointer to some data on a cache, it just returns one either on a database or a cache. And the elimination form of the union is just distributing the at over the union, or in another way, just converting it to either. Then you can just use the standard library functions that are provided by Scala to deal with these two either. You can do pattern matches. You can do whatever you want with that. Right. So how did we evaluate it? Well, this is fun, but is this an actual thing? We went around to see how people usually implement dynamic placement, and we particularly found that people like to use URLs to encode dynamic placement as strings, which is not very surprising because we want to place resources, and the R in URLs is the resources, and the L is for location, right? So at least the name seems to fit. But let me show you one particular example. I don't expect you to read all this code. However, this will be the first OOPSLA slide with a poem reading. And it says, the developer wrote, "I don't like storage. I'm sorry, poor developer. This is all my fault." And if you take a look, there's a lot of string manipulation going on, which I guess portrays the frustration of the developer. And to James, we say, well, we're here. You don't have to suffer anymore. So how did we find this code? We went through the open source projects in F-Droid. There's about 3,000 of them. And we found that 133 use URLs for dynamic placement. But I should also say that there are many ways to encode dynamic placement, and URLs is just one of them. And we didn't look for the others. I think 133 is a good sample to show that this is a real-world problem. And some examples are in F-Droid itself. So F-Droid checks whether some repository is local or not through checking the URL of the repository to disable some sharing, because you cannot share a local repository. VLC's source code also does the same. So VLC is a media player. And Element, which is a group chat, also does this, except that they added a comment saying that if we don't do this, then this runtime exception happens. And yeah, of course, we don't like that. You can see the GitHub issue. But one particular application which we wanted to, which we focused on, is a cool podcast manager application. It's quite popular, have 500,000 downloads, 5,000 stars, 8,000 comments, so quite actively developed. And in there, AntennaPod runs on your phone. It also stores some episodes of some podcast on your local file system, and it uses your local speaker, well, the speaker of the phone, to play some of the episodes. But it could also cast to a device remotely to play the episode remotely. So what you could do is, for example, you can have your local song or episode on your local device, and since you use URLs, you can point to it using a URL. And if you tell it to play it locally, well, the speaker can access your local file system, so that's all right. Except sometimes you may want to tell it to play remotely. And we found out that the AntennaPod developers were smart enough to realize that you cannot do that, except in one particular case, because there's all of these peers that need to be coordinated to make sure that you don't play files which are not available locally, remotely, but they've missed out on one particular path. We described this path in the paper. But essentially what this allows you to do is that you can tell it to play remotely, and it just ends up playing completely the wrong file, which is, of course, a bug. So what did we do? We just took the core of AntennaPod, which is just essentially the logic of distributing and storing these applications. We rewrote them in Dino. Dino is the DSL we have. And what essentially it does is that it keeps the URL, but it also has a reference. So it can point to the correct file. And since these are remote references, they can also cross boundaries. So we don't get the previous error as before. We've also checked whether Dino introduces a big performance overhead. And we compared it with RMI because RMI also has remote references. Dino and RMI both run on JVM. And what we implemented is a simple database cache application where you might get some sort of percentage on a cache hit or not inside of the database. And we just ran 2,500 queries. This is in red, Dino being the solid line, RMI being the dashed line, and in blue, which represent 5,000 queries, and we plotted them against time, and we see that, well, Dino does not introduce all that much runtime overhead, well, barely noticeable. That I kind of encourage you to go read the paper. It's a fun paper. There's inside it much more case studies, much more evaluations. We describe a little bit how we went around with the implementation, of course, some formalism and theorems with the proofs left to the appendix, not to the reader. All right. With that, in conclusion, the idea is that by taking ideas from type systems and applying them to placement systems, we are kind of developing richer and richer placement systems that are able to express more things. If you have questions, please go ahead and ask them.
So, again, you can use the mic. Well, in the meantime, I ask you a question.
Yeah.
Have you considered to basically introduce, how would you call it, inference, so that I don't need to annotate every single thing like server, infer in some of the types? You could, so that you don't have to annotate everything as server, client, cache. That you could have some inference mechanism?
So we don't do inference because the whole point of the because kind of the whole point is to make sure that
It's strong.
Yeah, the system is correct and implements what we expect it to implement. Although I think there was some work around inference.
Okay.
But we just want to make sure that, for example, you don't leak onto some peer that you don't trust some other information.
So you have the types that show that it could be either there or there. But if you want to encode in the program decisions on where to put things, how does your system interact with these kinds of decisions? Then just the either types manual programming, or do you have any libraries help us for also making decision where to store something?
Not yet, but you're free to develop these libraries if you want.
Thank you.
Thanks, Ragnar.
Okay, thank you, George.